often the improper integrals appear on the AP exam with direction something like this. So it'll either say something like evaluate the integral without hinting that it is an improper integral, or the directions could say state if the integral converges or diverges. And sometimes it's a mixture of the two. So sometimes they will outright say, evaluate the integral. If it diverges, state it diverges. Or if it converges, state that it converges. Or simply show that this integral diverges, things like that. And without that vocabulary, we would still have an improper integral. So when we look at this, we note that infinity is an improper limit of integration. Since this is an improper limit of integration, I know that I have to evaluate this improper integral. And something that has to be shown on a free response question on the AP exam is the algebra that transforms this improper integral into a proper integral. So what we do is we rewrite the exact same integrand and change as necessary the limits of integration. So that's a deliberately ambiguous statement, as you'll see when we look at another problem here. But for right now, we've got this one. And when we look at this one, and we're thinking about finding an antiderivative here so that we can apply the fundamental theorem of calculus, we must revisit the list of techniques. And we want to have an encyclopedic recall of these, and not just an encyclopedic recall of these, but like an electronic encyclopedic recall, because we want to be able to recall all of these fast. And we want to have a lot of comfort and familiarity with these because that allows us to evaluate these quickly. So as someone who is experienced and of course prepared, I look at something like this and I think through the different possibilities, and I might think about a little bit for substitution, but when I look at the denominator, the derivative 2x plus 4 doesn't really work out with the numerator. So then I might be thinking something like, oh, I don't know, completing the square. And completing the square, does it work? Well, it does not, because b is 4, and b divided by 2 squared is 4, so I have to add 4 and subtract 4, which makes this minus 1. Now, you don't necessarily have to go through it as a progression of things to cross off, but it is useful, especially when you're practicing, to take that opportunity to review any possible anti-differentiation techniques that could apply. So to do this, I'm actually going to need partial fractions, and the factors of x squared plus 4x plus 3 are x plus 1, that quantity, times x plus 3. So I have two terms, and I don't know the numerator for either term, but if I get a least common denominator of x plus 1, x plus 3, I will have a solvable rational equation. So x cannot equal -1 or -3. So I'm not writing out the algebra here to get solvable, but the short version is I multiply the first fraction on the right side by x plus 3 over x plus 3, and the second fraction by x plus 1 over x plus 1. This allows me then to use the shortcut. So if x is -1, I have 2 equals 2a because that's 0. Therefore, a is 1. If x is -3, I have 2 equals 0a and -2b, so b is -1. So we have an integrand that consists of this, 2 fractions. And you could do minus. I usually like to write -1 in the numerator because it makes it easier to remember how to do the algebra later on correctly. But in either case, both of these can be done with substitution. I won't write out all of the work, but it is not necessary to write out all of the work with substitution, but it is useful to think about substitution because it can sometimes reveal to you circumstances where you may need a constant multiple that you wouldn't otherwise consider. So we have the natural log of the absolute value of x plus 1 minus the natural log of the absolute value of x plus 3 from 0 to b. So my advice is to apply log properties, and I'm going to show you why. But first, let's apply them. So we have x plus 1 in the numerator, x plus 3 in the denominator, and we want to evaluate from 0 to b. So we have the limit as b approaches infinity of the natural log, the absolute value of b plus 1, divided by b plus 3, minus the natural log of the absolute value of 1/3. So we have a limit to evaluate. B is approaching infinity. For the natural log of the absolute value of b plus 1 divided by b plus 3. And to evaluate that, we are going to need to think about our log properties. So briefly, absolute value of 1/3 is 1/3. So I'm just going to write it as the natural log of 1/3 from now on. So how do we evaluate this limit? Well, it's been a while, but we consider this component first. So if we can do the limit as b approaches infinity of b plus 1 over b plus 3, which we can, then we will be able to successfully evaluate the entire integral. And I'm noticing here right away, even though it's been a while, that L'Hopital's rule applies because both the numerator and denominator approach something infinite. So I can apply L'Hopital's rule, which means I take the derivative of the numerator, which is 1, and the derivative of the denominator, which is also 1. So this has a value of 1. That allows me to rewrite that as 1. So I have the limit as b approaches infinity of the natural log, the absolute value of 1, minus the natural log of 1/3. And because I'm aware that the natural log of 1 is 0, I end up with 0 minus the natural log of 1/3. Since the result of the integral is finite. This integral converges. I mentioned at the beginning that I would explain why we would want to use log properties here. The reason why we want to use log properties here is because if we don't, we sometimes end up with an ambiguous result. Ambiguous in both the way the math is communicated and in the way our analysis may occur. So if I go back to the limit as b approaches infinity, of the natural log, the absolute value x plus 1 minus the natural log, the absolute value x plus 3 from 0 to b. This time, I'm not going to apply the properties of logarithms, and I'm going to look at this. Oops, I want parentheses there. Absolute value of 1 minus the natural log, the absolute value of 3. Okay, so when we look here at this, and we think about the limit as b approaches infinity here, we get infinity. And when we look at the second term as b approaches infinity, we get infinity. So we have infinity minus infinity. And it's really tempting to say that is 0. But we can't effectively say that in all cases, because there are some times where infinity minus infinity could very well be 0, but there are cases where this could end up being positive infinity, or this could end up being negative infinity. And to determine that does require some additional analysis. And in most cases, performing that additional analysis is quite challenging. So to summarize, what you'd want to do is compare the relative rates of growth. Now, we could do that here in a pretty straightforward fashion, but doing that is actually equivalent to applying L'Hopital's rule on the unsimplified form. So generally, we don't want to do something like this because this is technically an indeterminate form. And when we have indeterminate forms, well, we haven't studied this particular concept recently. We know that generally we want to use algebra to remove that from consideration. And the algebra that removes that consideration is applying log properties. Now, another benefit to doing that is for the expression, the natural log of 1 minus the natural log of 3, that allows us to determine that is a natural log of 1/3. And there are occasions for sure, say multiple choice problems, and while you don't have to show all of this algebra on a multiple choice problem, you may very well end up with this as one of the possible answer choices. And if you have not familiarized yourself recently with this log property, you may very well get lost. Now, not everything is a full page, but I will tell you that in general, writing the algebraic proof for these improper integrals can take a while. They are quite weighty, beefy, if you will. So this is another variation of an improper integral. And the integrand on its face doesn't look too problematic, and the limits of integration on their face don't look too problematic. But this is an example of an improper integral because for the function 1 divided by x, you have unbounded area approaching 0. And that, math friends, is what causes our issue. So the limit of integration here, the lower limit of integration here, 0, even though it is not explicitly infinite, it is implicitly infinite. And this forces us to rewrite our integrand like so. So we're still going to apply our knowledge of limits, but we're going to do it in a very different way. So rather than approaching infinity for b is going to approach 0, not just approach 0, but b is going to approach 0 from the left. Why is b approaching 0 from the left rather than infinity or something like that? And that has to do with the interval as given as 0 to 1. So if I'm on this interval, I'm considering no values less than 0. So I cannot approach from the left. I can only approach 0 from the right. So with that being said, we have the limit as b approaches 0 from the left. Antiderivative here is the natural log, the absolute value of x. We're evaluating from b to 1 this time. So what we're looking at is the natural log of 1, because the absolute value of 1 is 1, minus the limit as b approaches infinity of, I'm sorry, not infinity, my mistake, 0 from the left, the natural log of b. Knowing our log properties or values, the natural log 1 is 0, and now we arrive at a particularly difficult consideration. This limit. So how are we going to evaluate this limit? Because we can't really say b is 0, because the natural log of 0 does not exist. Like, it's not even not real. It just plain old doesn't exist. It's an impossibility. It is an impossibility. It's an impossibility because there is no power to which you can raise a number to equal 0. It's just impossible. So e to no powers exist equals 0. So how are we going to do this? And as I've illustrated for some other problems, it is beneficial to think about some common graphs. In this case, the natural log function graph. If we have the natural log function graph, it does allow us to consider the behavior of this function as x approaches 0 from the right, excuse me. Holy cow. In case you've been wondering, yes, that should be a positive sign. We can only approach from the right because only values larger than 0 from the right. So pretty much every time I just did that in the recording, well, kind of a problem, huh? Anyway, looking at this graph, we can determine as x approaches 0 from the right that this graph is approaching negative infinity. So we have 0 minus negative infinity which is infinity. This is an infinite value. Our conclusion then is that this integral diverges. So we have another function, and we look at it, and this one is interesting because the left endpoint is not an issue. We can approach 0 from the right. It's perfectly fine. We can approach 3 from the left. That's perfectly fine. Neither of these are a problem. Neither of these, limits of integration are a problem. So why is this considered an improper integral? This is an improper integral because at x equals 1, the function is undefined. So we, in fact, have unbounded area. And this existence of unbounded area means we have an improper integral. So this improper integral is a tricky one. We have to look at not the integral from 0 to 3 for this function, but we have to do this on 2 separate intervals from 0 to 1 and 1 to 3. And it's possible that one or both of these areas, which these integrals represent, could represent either finite area or infinite area. And even though we had to create this, other than having to write 2 slightly different limit statements, we don't have to do a whole lot more and different work from what we've done before. So what do I mean by that? I mean, we still have to write both of these as the limit statement. So I'm going to use B for this first one. This time I'm going to be careful. Unlike my previous mistake, I'm going to think about this interval. It's from 0 to 1. And we can only approach 0, sorry, not 0, 1 for the first integral. We can only approach 1 because it's the right endpoint from the left. So we're going from 0 to B. And while it doesn't matter too much, I still think that obeying the notational requirements of these being 2 different substitutions makes sense. So for the second integral, we are the interval starting at 1, stopping at 3. That means on this interval, we can only approach 3 from the right. Sorry, not 3. One. There we go. Okay. So we have written proper integrals. We can now apply the fundamental theorem of calculus. And we can apply the fundamental theorem of calculus here using substitution. Although it is possible by this point in time, you have reached to the level of experience where there are certain substitutions you can do without writing them down. I still contend, even if you're not writing them down, you should always think about applying substitution. Now, I'm not going to apply substitution here because, quite frankly, I don't want to deal with changing the variables for each integrand. But I am thinking about this nonetheless. So I wouldn't really write this ever on the AP exam. Probably wouldn't even write this on an opportunity to demonstrate mastery, but it is something you ought to be thinking about. Regardless, this is equivalent to thinking about something to the negative 2/3 power. So this is a power function. So I have the limit as b approaches that should have been 1. Good job by me. 1 from the left, antiderivative. So negative 2/3 add 1, positive 2/3 reciprocal 3 3 times quantity of x minus 1 to negative 1/3. That's evaluated from 0 to b. And same antiderivative, 3 times quantity of x minus 1 to the negative 1/3 power from a to 3. Now, my advice, as always, is to remember that negative exponents are disgusting to work with. So it makes a lot of sense to do this. And for me personally, I don't think it makes a difference to think of it as the 1/3 power or the cubed root. Your mileage may vary, but I do think that this is beneficial. So I'm going to have, after applying the fundamental theorem of calculus here, 2 terms, and here 2 more terms for a grand total of 4 terms. So I have the limit as b approaches 1 from the left of 3 divided by b minus 1 to the 1/3 minus, I don't need the limit here, 3 divided by negative 1 because evaluating this function at 0 means we have a that's stupendous. This is the wrong antiderivative. Positive 1/3. So I guess we can forget all my concerns about negative exponents. That's b minus 1 to the 1/3 power minus 3 times negative 1 to negative 3 plus 3 times 3 minus 1 is 2 to the 1/3 power minus the limit as b approaches 1 from the right, 3 times b minus 1 to the 1/3. A little bit tiny there. Sorry about my anti-differentiation goof. We do have an easier analysis to perform though, because we can evaluate both limit statements with substitution. Both of them are 0. So I have 0 for the first term, plus 3 for the second term, for the third term 6, and for the final term 0. So I have 9. That means that this integral converges. After finishing the problem, I noticed a mistake. The mistake was right here. Even though I correctly wrote 3 times 2 to the negative 1/3 power, I ignored that 2 to the, I'm sorry, positive 1/3 power. I completely ignored that here when I wrote 6. So we should have 3 plus 3 times 2 to the 1/3 power. And I certainly don't advise this, but it is possible that you might see something like this. And honestly, I wouldn't worry about that for a second on a free response question, but multiple choice questions are half the exam. That concludes our practice problems looking at the improper integrals. So we had a real beefy one, and this was a beefy one because we had not just an improper integral, but log properties, L'Hopital's rule. And that made for a much longer problem after finding an antiderivative with partial fractions. And we did a couple of others. These ones were sneaky improper fractions. Our first one was an improper fraction because the left endpoint of the interval, the lower limit of integration, made the function undefined. So it's a discontinuity. And the second one was also sneaky because neither endpoint was a problem, but the interval was. Now, if this interval was from 1 to 3, I would have only had a single limit statement to write. I would have approached 1 from the right. And if this integral was from any interval not containing 1, like say from, I don't know, -1 to 0, -5 to -1, 10 to 12, anything else, we wouldn't have had an improper integral whatsoever. I hope you enjoy studying these problems and that you have gained something from their consideration.